Welcome to Hot Chips 27. Session 3, High Performance and Cloud Computing and Communication.
Okay. Welcome to...
Okay.
Yep. Hang on, Charles. I will introduce the session and then hand it over to you. So just a couple more minutes.
Okay. Can you speak aloud? Small voice.
Okay. So I'm Sam Nafziger from AMD, and I will be chairing the final session of the day titled High Performance, Cloud Computing, and Communication. We have a number of interesting and ambitious designs here from diverse technology areas to cover, and some exciting new revelations. So as you may have gathered by the live feed, our initial presenter was not able to be present here in person. We had a visa challenge from mainland China that we couldn't work through, and we had a plan A, B, and C regarding getting a video feed through the Great Firewall and Google Hangouts, and the audio file that was pre-recorded was too large to make it through the email server. So now we are down on plan C or D, I'm not quite sure which one, but we have a telephone connection and our presenter is live on the line, as you have heard. And the title of his talk is Mars, a 64-core ARM V8 processor. So we are excited to hear what Phytium has accomplished here in this design. So our speaker is, just a minute here, let me find it. Is on the line from mainland China, and will be, he has graduated with his PhD from the Hunan University in China, and working with Phytium since 2012, and is the director of research there. So without further ado, Charles, I will hand it over to you to begin the talk, and I will flip the slides as you tell me. So Charles, please commence your presentation.
Yes, you can project it. So, is my voice heard by the corner in the office, in the conference room?
You are coming through loud and clear.
So, I must speak aloud.
We can hear you just fine.
Am I heard?
We can hear you just fine, Charles. Sounds very good.
Okay. Okay, I'm beginning right. Hello, everyone. Hello. I can begin. Hello, Sam.
Yes, everyone can hear. Please begin the talk.
Okay. Hello, I'm Charles Zhang from Phytium. Good afternoon. So it's a little stranger to say good afternoon in the morning. So it's just 7 a.m. in China. And I must say sorry to give this presentation in such a way. Due to my visa problem, I cannot attend this conference on site. It's a pity. So thanks to Sam and his staff. They are very dedicated and very professional, even if I have suffered too. So Oxford situation, they still give me this chance to introduce all my recent work to you. So okay, let's back to the point. So Max is a 64 cores ARM-V8 processor, and I'm pretty sure this will be the first 64 core ARM processor in the world. Okay, Sam, please, next slide.
Yes.
So this is some legal statements. We can skip this quickly. Next. So I think it's necessary to give a brief introduction of Phytium. Maybe Phytium is a very new face to you. Indeed, Phytium was just founded in 2012 and have no products on the market yet. Now it has two offices. One is in Guangzhou and one is in Tianjin. Yes, Tianjin. Yeah. So you're correct that the city where happened a miserable explosion recently. Our office is only 15 kilometers from the accident location. So Phytium's vision is to deliver leading-edge Chinese CPUs and ASICs to local users. Now it focuses on Chinese markets, especially the chief market for internet and cloud computing infrastructure and some traditional mainframe servers. Of course, if any international partners consider our products are interesting, are suitable for their system, we are happy to talk cooperation. So next slide. As we all know, China is a very big market and fast growing. So the server will be no exception. This chart is from Gartner this year. You can see it's a year-over-year server sales growth worldwide is about 18%. But in China, the year-over-year growth is about 23%. So among these providers, the local providers such as Inspur, Lenovo, Huawei, Shogong shared almost half the China market. So these are all Phytium's potential chip users. Of course, these fields are all from x86 servers, but we think ARM still has opportunity, especially considering the low power DIMMs and the flexibility for partners. So next slide. Okay, typically we can categorize a server into three parts according to the scale form. As we all know, scale out, scale up, and clusters. So scale up is getting taller and taller, stronger and stronger. Processors are tightly coupled to support shared memory. So mainframe cabinets fall into this category. On the contrary, scale out is getting faster and faster. Each node may be not very strong, but bundled together, they can still provide strong powers. Processors are loosely coupled to connected with Ethernet or other commercial networks such as InfiniBand. So blades fall into this category. But the scale up is set to easy to program, but hard to scale. Well, the scale up servers is easy to scale, but hard to program. So for processor providers, CPUs or scale up servers usually hold these features on the top of the slide. It must deliver high performance and also support high volume of memory, provides the high bandwidth memory and I/O access, large scale caches, coherence maintained. better by hardware because it's easy to program. Well, a scale-out server CPU holds features like moderate performance, but low power, which can result in the high power efficiency, and high-density computing to easily equip into a limited space, and also high bandwidth memory access. Another very important factor, the low cost is very important too because it can get the upgrade very easy. So Mars is designed for scale-up server usage. We will talk more details next. First, it's designed for scale-out servers, which is not our point today. So the next slide. So let's first take a quick look at Mars features. It has integrated 64 Xiaomi cores on chip. Xiaomi Core is designed by ourselves and compatible with ARM-V8 ISA. Mars supports hardware maintain global cache coherency across all the 64 cores. 64 cores are partitioned into 8 titles, as we can see on the diagram. Different memory space, different I/O devices are mapped onto different panels, which we call this panel-based data affinity architecture. 8 panels are interconnected with a 2-dimension mesh on-chip network. Mars has totally 32 megabytes level 2 cache on chip. It also has level 3 cache, but level 3 cache is not on chip. It resides on another couple's chip we call CMC, the cache memory chips. So 8 CMC chips are connected with Mars, providing total 128 level 3 cache and 16 DDR3 channels, providing 204 gigabytes per second memory access bandwidth. Mars also provides 216-line PCIe Gen 3 interface, providing 32 gigabytes per second I/O bandwidth. As Mars will be used in server workloads, so rest is very important for it. ECC and parity protects all RAMs in Mars, such as TLB, tags, cache, and so on. Mars will be taped out on 28 nanometer process node. After physical design, Mars consists of about 180 million instances running at 2 gigahertz, which can delivering 512 T-flops peak floating point performance at this frequency and consuming about 120 watts typically. So the next slide. Till now, am I clear? My
Yes.
voice is heard?
Yes,
Okay.
it's going well.
I'll go on. Okay. So we will go some details about Mars architecture. First, let us see the panel architecture. Each panel consists of 8 Xiaomi cores, 2 level 2 caches. Size is totally 4 megabytes, and 2 directory control units, which is DCU for cache coherency maintenance, and a routing cell for interconnect among panels. After PR, a panel looks like this. The right bottom floor plan is about 10,600 micrometers high and 6,000 micrometers wide. So 4 cores and a level 2 cache on the top and on the bottom. In the middle is 2 DCU and a routing cell. So that there are some logics spread into level 2 because the routing cell must connect the 4 directions. Xiaomi is in-house designed ARMv8 compatible cores based on an architecture license. It implements both AH32 mode and AH64 mode and all the exception levels. Xiaomi is equipped with 4-wide fetch, 4-wide decode, and 4-wide dispatch out-of-order superscalar pipeline, which also equipped advanced branch prediction in the front end of the pipeline and two-way ascend supported in the function unit. So the next. So this is the internal structure diagram of Xiaomi cores. It's a very classic superscalar pipeline, separated level 1 instruction cache and level 1 data cache, and branch prediction in the front end coupled with the back end by the instruction buffers. Rename logic to remove the anti-dependency and output dependency. Reorder buffer to keep the right program order. Instruction queue or reservation to hold the operations waiting for their operand. Pipeline function units for different instruction types. Prefetch to reduce instruction cache and data cache miss penalty. Of course, for compatible with ARM architecture definition, Xiaomi also implements debug, trace, interrupt controller, and timers, etc. So next slide. In the front end, instruction cache has 32 kilobytes inside and 4-way set associative, and its PIPT accessed each cycle. 4 instructions take 2 cycles to read out from the instruction cache if hit. When missed, a level 2 cache access initiated and a next line prefetch is done simultaneously. Several mature branch predictors are used, such as BTD, RAS, and indirect prediction. Xiaomi also implements the tag-based direction predictor, which can provide the accurate by 3 to 5% in average versus the traditional branch predictor. Instruction buffer acts as a loop buffer as well. Loop detection tries to find out loop patterns and hold them in instruction buffer. When the loop detected, instruction cache can be bypassed and the decoding logic are fed by instruction buffer. This will reduce the instruction cache access time and power. So the next, slide 10. So this is the middle stage of the pipeline. Instruction is still processed in order. Up to 4 instructions decoded per cycle, up to 4 instructions renamed per cycle, and up to 4 instructions dispatched to the corresponding instruction queue per cycle. Registers are provided into 2 categories, architecture register file and physical register file. Source operand can be read from both register file in order to remove anti-dependency and output dependency. 192 physical registers are provided for destination renaming. Registers will be updated from the physical file to the architecture register file only when corresponding instructions retired. The register file is very critical resources because up to 4 instructions can read register file in parallel. In ARM ISA, there are some 4 source operand instructions, thus resulting in 16 reading ports to the register file. It's a very complex design. To reduce the complexity, Xiaomi implements a 12 read ports register file. Some ports are dedicated and some are shared among the 4 dispatch slots. This will reduce the area of core by about 2.5%, and fast only 0.17% performance overhead. The reorder buffer has totally about 116 entries, which can hold 116 instructions. In other words, instruction level parallelism can be exploited among these 160 instructions. If we take the pipeline stage and buffers into account, more than 200 instructions can be in flight across the whole pipeline. So next slide, slide 11. From the instruction queue, the pipeline enters an auto-order execution slide. Separated instruction queues can independently issue instructions to affiliate function units whenever the instructions are ready to issue. For integer units to floating point units, one load units and one load store units are equipped. Two of the integer units can process single cycle instructions. One of them can process branch instruction 2. If we bundle these two integer units together, these two integer units can process single cycle integer 128-bit ASMD instructions. The other two integer units can process multi-cycle integer instructions, and multi-cycle integer 128-bit ASMD instructions in the same way. So here is a little difference from the version I proposed to hot chips last month. If it has been distributed to you, I have clarified with Red's design guides. It was my misunderstanding that time. I'm sure this version is right. Sorry for the confusion. And for the floating point units, they have the same organization for floating point 128-bit ASMD instructions. Floating point units supports the pipeline fuse, multiply, and add with a latency of 6 cycles. At most, 4 double precision floating point operations can be processed per cycle. So next slide. In load store units, 2 loads or 1 load and 1 store can be issued simultaneously. Data cache is also 32 kilobytes in size, two-way size associative. It is non-blocking and can support 6 outstanding loads. From loads to use, it takes 4 cycles when hit. Thread-based data prefetch is supported, and the next line prefetch is the default pattern. To avoid cache pollution, stream data access pattern is auto-detected and force them to non-cacheable attribute. So this is Xiaomi Core Decode architecture, more aggressive ITLB exploitation than most of current ARM-compatible cores. As we will see, Xiaomi Core can deliver higher single-thread performance. Okay, the next slide.
Charles, 4 minutes.
So,
Charles, 4 minutes to go. Just.
Okay. So, sorry. Can you hear me?
We can hear you. Just 4 minutes left in time.
4 minutes.
That's right. Please continue.
Okay. Let's say the cache coherency protocol in Mars. Codename is HOT. Mars implements a directory-based multi-like global cache coherency protocol. The directory is distributed across all the panel level 2 cache as we talk. Physical memory space that is a CMC are affinitively mapped to each panel. We call the level 2 cache or the bundled DCU or the coupled for Xiaomi cores the home node of the affinitively mapped space onto them. Each DCU is responsible for and only for managing all the affinitive memory space, no matter one of the addresses is accessed by local cores or by the remote cores. So, but due to the limit size of directory, the local access cache line have higher priority to reside than the remote only access cache lines. When one level 2 cache is asking for affinitively memory access, it checks the local DCU to find the corresponding states enriched by local CMC or get copies from other level 2 cache. When asking for a non-affinitive memory access, it goes to the home node DCU to check the corresponding states generated by remote CMC or get copies from other level 2 cache. I will skip some details. So the next slide is the on-chip network. Must use a two-dimension concentrated mesh network to connect each panels. It contains 8 basic routing cells, 4 in a row and 2 in a column. And in average, from one node to the other nodes, it will take every 9 cycles in average on the network side. So the next slide. So to deliver high bandwidth or memory access, more and more DDR controllers are integrated onto CPU chips, but limited by package pins. It's difficult to integrate more than 8 DDR controllers. To solve this problem, Mars used coupled cache and memory chips to scale the memory bandwidth with computer powers. And one Mars chip can connect 8 CMC chips. So the next slide. So the frequency of the panel and NOC are both run at 2 gigahertz, and the frequency of CMC is 1.5 gigahertz. And if the access hit affinitively, only several nanoseconds used to get the right data back. So the next slide, 17. So we also expand some performance monitor and profile registers on chips, such as the number of cache hits misses in level 1, level 2, and level 3 cache workload level or cache pipeline, etc. We call all these expanded registers and counters the mTune. With this metric, we can do some advanced analysis, including the CMAT analysis and some MPI and open MP application analysis. So the next slide. So this here is debug over the network, because if we set up debug system only use ARM core set components, it will result in many long wires, making the physical design bothering. To solve this problem with debug over network. Okay, the next slide. Now we have almost finished the physical design of Mars. Mars is built at 28 nanometer precise. Many types of stem cells, including multi-VT and multi-channel length, multi-tracks, and multi-vendors stem cell and SRAM are used to meet the PPA target. So this is the Mars floor plan is just almost a square. So and we will use FCBDA package with 3,000 pins, and in which about 1,000 pins are single I/O pins. So the next slide. So we do some on the hardware emulator and FPGA prototypes. We do some preliminary performance evaluation, SPARC CPU is the most popular. So this is the left is the single copy of SPARC CPU 2006, and the right chart is for the 64 copies of SPARC benchmark. So we can say it's especially the single copy scores only about 1/3 to 1/4 of the mainstream high performance processors, but the parallel performance is very good, especially accounting for the power of consuming. So the next slide. To measure the memory accessibility, we run the stream benchmarks at all scales. We can see Mars demonstrate a near linear scaling from core to panel to chip. So of course, if we do stream copy at scale or shared across the panels, it will illustrate obvious decline or efficiency. So the next slide. So it's not a very spectacular score or format, but for us it's good. It's a good beginning. In the next few years, we will continue to develop more powerful scale-up CPUs, taking Mars as a basement. So okay, thank you. Any questions?
Yes, thank the speaker. Yeah. Charles, we have time for perhaps...
Okay, I'm here.
Yeah, we have time for one or at most two questions, and if people use the microphone, Charles should be able to hear.
Okay.
Question about the Earth processor that was shown on the first slide. Is that being designed by Phytium as well, or what is the Earth processor?
Which slide? Which page?
I think it was slide 3.
3? Slide 3.
Or sorry, slide 5.
Slide 3.
Yeah. No, slide 5. What is the nature of the Earth processor?
Okay. So the Earth, I'm not authorized to disclose any features of Earth. So I cannot to talk about Earth in public. So maybe we can, if this audience is very interested about Earth, we can communicate by emails or face-to-face, if possible. Okay.
Okay, and we are over time, so Charles, we thank you for your time and the presentation.
Okay. Thank you again, and sorry for giving this presentation in such a way and bring you many troubles. So, but very sorry.
It worked very well. Thanks again.
Okay, thank you. Bye.
Okay. We will move on to the next talk, which is titled the LS2085A, Freescale's new QorIQ Layerscape Communications Processor. And this will be presented by Zhang Xu of Freescale. He is currently the Chief Engineer of Freescale Digital Networking Hardware Technology Division, and he leads their next generation networking architecture and new product definition. And he was the chief architect of this design and several other QorIQ communication processors in the past. So without further ado, I will hand it over to John.
Thank you, Sam. Well, I'm very excited to be here to present Layerscape 2085, the new QorIQ Layerscape communication processor from Freescale. this is the agenda. After a quick introduction, I will dive into the LS 2085 details with a special focus on the data path acceleration subsystem. And after that, I will show a few example application use cases followed by the performance results. Software-defined networking and network functional virtualization are the new megatrends of the networking industry. The new virtualized network needs to be flexible for auto-provisioning and faster deployment. And it also calls for interoperability between the vendors. And it needs to be compliant to the open networking standard. While we, the networking industry, are facing this new deployment paradigm, as a chip vendor, we also have our own issues. We have additional constraints we need to take into account in our architecture and design choices. First, it's still about performance per watt. It's about how to produce the best performance under the tight power envelope. And the networking I/O bandwidth is increasing drastically from 1 gigabits per second, 10 gigabits per second, 25 gigabits per second, and to 100 gigabits per second. To some extent, this is faster than we can pack the many cores on a single die to consume those network traffic. And also the last, and also very important, the general multi-core design still face software challenges to take advantages of its full potential. Specifically, SDN data plane processing has its unique challenges. You cannot simply by putting many cores packed on a single die and resort to a pure software approach for table-based flow processing. A pure software approach, such solution, typically sees performance cliff for thousands of flows with small packets and for large forwarding table with million entries. And acceleration for the critical networking functions, such as table-based flow processing, switching, security, compression, those are very, very important to meet the deterministic and power performance efficiency requirement. On the other hand, data plane processing and protocol offloading, they needs to be highly programmable to adapt to this ever-changing new open networking standards, such as OpenFlow, and also to this ever-evolving software references, such as OVS for virtual switching. So Freescale's solution to this SDN and NFV challenges is a new QorIQ Layerscape architecture, which balanced multi-core general-purpose processing with highly programmable packet processing with acceleration and focusing on ease of use and power performance efficiency. The Layerscape architecture is core agnostic. We support ARMv8 core and we support PowerPC cores. And it has this new scalable architecture for data path acceleration, including a new programmable and advanced I/O processor. And it has support for advanced switching, as well as abstraction of the I/O and acceleration. This architecture is driven top-down from system and software perspective. And it uses industry standard tools, and it includes turnkey software as part of the solution. With that, let me introduce Layerscape 2085 chip. This is the flagship chip of the QorIQ Layerscape architecture. We spent 2 years to develop the technologies for LS 2085, and we have successfully sampled it February this year. And we are about to go into production with actually Rev 1 silicon shortly. So that's talk about more details of LS2085. LS2085 features 8 A72 cores with 2 cores sharing 1 megabyte L2 in each cluster. It also has 1 megabyte of L3, which is mostly exclusive to the upper-level caches. So the design choice of this 2-core cluster and cache sizing is based on the performance study of the networking workload we have. Instead of include a large last-level cache for this chip, we focus on the stashing support to the caches and bring the data from memory to the core processors just in time for its processing. And this chip also has a ring-style cache coherent interconnect. It has a lot of flexible network-on-chip interconnect design in the AXI fabric. The memory subsystem features 2 64-bit DDR4 controller up to 2.1 gig transfer per second. And furthermore, we have introduced a third DDR4 controller, which is 32-bit for data plane processing. In addition, we have introduced a large SRAM as a packet buffer, which efficiently connect different components of this networking acceleration subsystem. This on-chip SRAM is heavily bank interleaved, so it provides a huge amount of bandwidth, which is about 10x of the off-chip DRAM bandwidth. From the system connectivity perspective, it's not showing this is a slide, but we do support 16 Ethernet ports, and with 8 of them capable of 10 gig Ethernet. And we support 4 Gen 3 PCIe controller, as well as 2 USB 3.0 controller and 2 SATA 3.0 controller, and other miscellaneous interfaces. Let's dive a little bit more into this data path acceleration subsystem. The data path subsystem is fully virtualized and isolated. It has this address token support, which allows the software entity to connect to the network hardware accelerators, completely bypassing the kernel using the user space virtual address. And the accelerators is coherent with the core processors. There is no copy for the software to invoke the hardware accelerators. We also have this virtual switching capability in this data path subsystem. This virtual switching capability allows the software entity to connect to this acceleration functions in a service chaining style. This is very important for networking. And this data path subsystem has a new change. It has a new management complex hardware entity, which abstract I/O and acceleration. And we will go into more detail on this because this is actually a very important step in this data path architecture. And the queue manager, as part of, in the core of this data path subsystem, provides a highly efficient, high bandwidth event machine connections between these software entities and accelerators. It also provides packet level scheduling offloading. The AIOP is highly programmable. It's a C programmable packet engine for data plane processing and the protocol offloading for L3 to L7 level. The wide-rate IOP provide intelligent parsing, classification, distribution functions, as well as serving as the backbone of the physical and the virtual switching. This chip also includes several application-specific accelerators, such as 20 gigabits per second SEC engine, a 10 gigabits per second pattern match engine, and 20 gigabits per second compression engine. This is a couple of pictures about the RS-2085, the die floor plan, and also the package. Overall, we have packed over 2.2 billion transistors on this die in a TSMC 28 nanometer HPM technology. And it's working with 37.5 by 37.5 flip chip PBGA package. So at this point, I would like to pause a little bit. I think this session is about cloud computing and high performance. As you see that RS-2085 is not focusing on maximizing the general purpose performance. Rather, we focus on a balanced general purpose processing capability as well as programmable packet processing capability. So instead of pure cloud computing play, we focus on the networking and the storage to enable this cloud computing. Although our Layerscape architecture does have extension, we could cover server, but this is focusing on networking and the storage. And as you see, SDN and NFV are moving from data center to the WAN edge to the customer premise. And this chip, in addition to a lot of other traditional networking and storage applications, is very suitable for this virtual customer premise equipment, which has virtual workload running on general purpose processor coupled with programmable packet protocol offloading. So it's very suitable for this virtual CPE type of application. This is a little bit more detailed slides about management complex. So the idea is about ease of use and abstraction. On the left, you see there are a bunch of hardware accelerators with a lot of features. With the help of this newly introduced management complex hardware entity, specifically in the area of configuration, connection, discovery, resource management, we turn this bunch of hardware blocks into a few Layerscape objects. So one example is this data path network interface. And as you see in the right diagram, it provides easy connection to the user space or kernel drivers. So this is so easy, so it can allow a new user to jumpstart and start using and leverage more advanced data path features right away. A few more words about this new advanced I/O processor. So AIOP is a multi-core, multi-threaded packet processing engine. This particular version of AIOP can handle 256 threads at the same time for various different packet processing. And we are using our own PowerPC cores with a lot of customization to maximize this performance. We have introduced special instructions to accelerator for the hardware acceleration cores. And we have introduced additional forms of load store instructions to optimize the performance for file and forget statistic reporting type of applications. And AIOP has this hardware task scheduler, which is there to minimize the context switching latency and hide the accelerator core latency. And AIOP has this efficient DMA and hardware semaphore for deterministic performance. And the AIOP also, as you can see, it has a variety of tightly coupled accelerators for parsing classification, for table lookup, for algorithmic ACL, for timer management, as well as file and forget statistic reporting. Furthermore, AIOP has also this order synchronization, special order synchronization with parallel and atomicity ordering scope support to optimize this ordered packet flow processing. As a result, AIOP can perform a variety of the packet offload tasks at a fraction of the GPP software if you implement it as a pure software approach. And we have measured on silicon that AIOP provides 5x and more power performance efficiency than a pure software-based approach. This is this is a good example of AIOP program. It shows a little bit AIOP code snippet. It's really two hardware thread is running on this core for two different packets. So as you can see that this program is just like a straight C program. It's almost exactly the same as you would write it on the GPP, general purpose processor. So the hardware and also a little bit of service layer running on hardware is working under the hood to take care of all this context switching and hardware accelerator calls. If you want to call a hardware accelerator, you just need to make a function call and be done with it. You don't need to worry about when the task will come back. It will all be handled by the hardware. And when the accelerator has finished its processing, and the task scheduler will evaluate all the pending tasks, and it will schedule the next job to run on this processor cores when the time is right. So a little bit background about this task and the job. So task essentially is created by a work scheduler to accomplish some type of work. So in this case, it's a packet processing. A job is a task is a collection, can be break into a sequence of jobs, but the jobs share the same context. And the job is the minimal schedulable part of a task which will be executed by the processing element. In this case, it could be the core, it could be the accelerators. As a result, you see that at lower of the slide, the core is fully utilized and occupied by the software processing for different packets due to the hardware handling all the other acceleration and scheduling complexities. So as part of the overall Layerscape solution, we provide many turnkey and production-ready software packages on AIOP with easy GPP integration mediated by the management complex. We also provide Linux SDK with support of virtualization on general purpose processor with KVM, QEMU, Linux container, and all that good stuff. And we do support the industry standard toolchain. And very importantly, we are compatible with the industry standard acceleration APIs such as ODP. This is a slide to show a few example applications of Layerscape 2085. Started from enterprise router to a virtual customer premise equipment to the, you can use it for network analytics running NetFlow and BFD And you can use it as an intelligent NIC to offload the virtual switching and to offload the security, compression, those network functions. And also you can use this device as an open flow switch or as network appliances. So here are some silicon performance results we have measured. As you can see, the CoreMark and SpecInt results, it turned out to be as expected. For those benchmark are highly related with this 2 gigahertz A72 cores we have in this device. So they measured, they turned out to be as expected. The stream bandwidth is reasonably good compared to the alternative competition in the market. We do have some in-house proof point to characterize the networking performance. One of I'm showing 2 examples here. The complex IP forwarding is essentially, it implements the entire data forwarding plane with 5 table lookup, including ACL, including LPM, exact match. And for both complex IP forwarding and NetFlow packet processing proof points, we have demonstrated that we can meet the 50 gigabits per second at IMIX of packet size performance. This is a little picture about this LRS-2085 reference design board. And we have shipped many of this reference design board to our customers and partners. It has the connectors for the majority of the chip interfaces, such as 3 DIMM connectors, 4 10 gig Ethernet connectors, 2 PCIe connector, USB, SATA, and all the miscellaneous interfaces. So as a quick summary, we have illustrated the new QorIQ Layerscape architecture, and we have demonstrated LRS-2085, how LRS-2085 is there to meet the power, performance, efficiency challenges, as well as ease of use challenges. So I would like to take this opportunity to thank the Freescale digital networking hardware and the software team to make this LRS-2085 a reality. And very importantly, the successful Rev 1 production. And I would also like to thank the Hardchip program community for this good opportunity to share the information. So thank you very much. That's the end of my talk, and questions and comments welcome.
We have time for a few questions. You can use the mics to the left and right. While we wait, John, I had one. You had the power numbers in there and voltage and all. How much attention did you pay to power optimization and like standby power reduction? Do you have power gating in the design, for instance?
Yes. We do have power gating support for the core clusters and the AIOP processor engines. And we also have the DVS-FS type of power management support. And we use voltage ID to manage our product billing strategy, this type of thing. Because networking is typically designed for worst case condition. So what we focus on is really how to reduce our thermal design point for our worst case condition instead of a little bit different from the mobile market where you have a lot of runtime power management support.
Great. If there are no other questions, we will thank our speaker again.
Thank you.
The next talk we have, as you can see, is Oracle's Sonoma Processor, advanced low-cost SPARC processor for enterprise workloads. For this talk, we will have two presenters, and they will tag team. The first will be Basant. Basant Vinaik. He has a BS degree from Malviya National University in India, and over 20 years of industry experience, and he's been with Sun and Oracle for the last 14 years. He's currently working as a senior principal engineer in the SPARC processors group and focuses on all aspects of processor design verification. And about 15 minutes into the talk, he will hand it off to Rahoul Puri, who is an architect in the performance and architecture group at Oracle for over 7 years. And his focus is on networking and low latency I/O hardware and systems design. He has an MSEE from Auburn University and over 20 years in the industry. So with that, I will hand it over to Basant, our first speaker.
Thank you, Sam. Good afternoon, everyone. Today we are talking about Oracle's Sonoma Processor. It's an advanced low-cost SPARC processor for enterprise workloads. First, I will talk about CPU design, share some performance numbers with you, and some system design concepts. And later, Rahoul will talk about networking features of the chip. Legal disclaimer. Sonoma is the first of a new line of processors that will extend our current product lines and will provide enterprise-class performance and advanced software and silicon features to lower-cost form factors. Sonoma achieves this through some breakthrough system integration that provides excellent throughput, low memory latency, and high bandwidth networking interconnect. Sonoma is a powerful chip. It is optimized for a broad range of applications, such as horizontal scale databases, middleware, and cloud computing. Last year at Hot Chips, we disclosed our high-end M7 processor. It's a scale-up processor that provides extreme performance and scalability. Today, we give you our scale-out processor, Sonoma. It's fully integrated with memory, I/O, and networking. The functionality of all the chips that you see in this picture has been integrated into Sonoma. And it will provide extreme benefits to our customers by lowering latency, power, and cost for scale-out. Here is a bird's eye view of Sonoma. You can see how much technology we have packed into this chip. It contains 8 SPARC 4th generation cores, which are matched with the highly optimized cache organization. It provides advanced software and silicon features, such as application data integrity, memory migration, VA masking, and database hardware accelerator engines. It features direct attached DDR4 memory. It integrates PCI Gen 3 on chip. And new with Sonoma for SPARC processors is the integration of InfiniBand host channel adapters. And this provides a scale-out, low latency, high bandwidth networking interconnect. So Sonoma has all the building blocks for designing the next generation dense and highly efficient compute node. And by the time we are done with this presentation, you will see that Sonoma is the perfect choice for scale-out. So Sonoma provides high performance. This is achieved by integrating an enterprise-class core with built-in crypto and advanced software and silicon features. We have leveraged this core from our high-end M7 processor and was discussed last year at Hot Chips, so I will not go into many details. It contains an integrated crypto unit that provides user-level crypto instructions, such as listed here. Now, these instructions can be used directly in programs or in libraries such as OpenSSL. And these provides security acceleration and encryption throughout the software stack. The core also provides advanced software and silicon features. These are bits of software implemented in hardware. They're very low overhead and excellent applications. And we will talk about these features in details in some coming slide. So Sonoma's enterprise-class core is matched with the cache organization, which is optimized for latency and throughput. There are 2 SPARC core clusters on the chip. The picture shows one of them. It features a split level 2I and a level 2D cache design that allows us to provide a very high throughput of 500 gigabytes per second. It contains a large 8 megabyte L3 cache partition, which is designed to reduce latency and improve performance. There are 2 such cache partitions on the chip, and lines can be replicated, migrated, or even victimized from one partition to another. L3 also allows hardware accelerators, InfiniBand, and PCI DMAs to allocate lines in cache, and hence speed up DMA operations. So one key design feature that you will look for a chip designed for scale-out is whether it provides low memory latency. Sonoma achieves this by integrating DDR4 interfaces on chip. Typically, a CPU talks to memory via interface chips, also called BOB chips or buffer on board chips. Now, our design does not contain those, and hence it reduces latency from memory access paths. As seen in the picture, there are 2 memory control units which provide scheduling and physical interfaces for 2 high-speed DDR4 channels. And each of these channels can have up to 2 DIMMs per channel, and that provides for up to 1 terabyte memory per socket. So the removal of BOB chips reduces latency. We have reduced it even further by using another design feature called speculative memory read. When a line misses in an L3 cache partition, as you saw in the picture in the last slide, it sends a speculative request to memory even before the peer lookup is finished in peer partition. Now, this provides data prefetching by storing the data into prefer buffers built into the chip. This is done on a per transaction basis and utilizes the dynamic history of instruction and data type misses. And software can tune this using threshold registers. So enterprise class core, highly optimized cache organization, and low memory latency allows Sonoma to provide high performance for scale-out. Another key design feature that you will look for a chip designed for scale-out is its I/O connectivity. Does it provide flexibility, reliability, and density in rack space? Sonoma's connectivity is optimized for scale-out. The picture shows 2 Sonoma sockets communicating with each other. And each socket provides 2 InfiniBand links running at 14 data rate or aggregate 56 gigabits per second per link. It is these links that provide a scale-out, low latency, high bandwidth networking interconnect. Each socket also provides 2 PCI links running at Gen 3 rate, and this provides a lot of flexibility in designing connectivity to I/O peripherals. And finally, the 2 sockets communicate using scale-up coherence links, as seen in the middle of the picture. So Sonoma scales to 2 sockets directly. However, using the InfiniBand links, it can scale to thousands of sockets. Yet another key feature that you will look for a scale-out chip is whether it consumes low power. Sonoma achieves this by a fine-grained control on power management. The picture gives you design concepts for doing that. Each core and L3 cache contains a fine-grained power estimator called self-governing core, which tracks internal activities to estimate dynamic power. And then it gives these estimates to a central power management controller, or PMC. PMC is responsible for estimating the power of the core, caches, and SoC. And PMC does that by interfacing with sensors, such as temperature and current, and then provides dynamic voltage and frequency scaling. Now, all this is controlled by thresholds set by software-defined policies, which could be limiting power, current, temperature. Now, this fine-grained design allows us to optimize for a lower TDP or a thermal design power. And it also helps us to simplify system design, as we don't require customized cooling or customized large power supplies. And hence, it reduces system design cost. Now let's look at some advanced software and silicon features that I touched upon in an earlier slide. One key feature is called Application Data Integrity, or ADI. Now, ADI protects against software problems such as stale pointers, invalid references, buffer overruns. It also provides real-time application security against malicious hacker attacks, such as the one seen with Heartbleed. The picture gives you basic concepts of how ADI works. Each 64-byte block of data is given a version metadata, which is stored in memory and maintained across caches and interfaces. Each load or store instruction that needs to access this block of data needs to provide a version metadata as part of its virtual address. So if the instruction's version matches with the reference version in memory, the access is allowed. If not, the access is killed and logged, and applications can take necessary recovery actions. Now, this feature can be used by programmers while developing their code, and then it is turned on in production environment to provide real-time application data integrity. So when you take ADI and couple it with integrated crypto in Core, it provides a very powerful and secure cloud computing environment. Another key design feature for software in silicon is Database Analytics Accelerator, or DAX. There are 4 such hardware accelerators built into the chip. It is multi-threaded and contains 4 pipes, so total 16 DAX streams can be simultaneously active with Core. Now, DAX works on in-memory columnar vectors, which could be compressed or uncompressed. As seen in the picture, DAX receives its input data from memory or cache, performs the desired analytics, and then writes the result back to memory or cache. Some of the analytics performed by DAX include in-memory format conversions, that is converting from one format to another, or value or range comparisons, comparing different fields in different tables, or set membership lookups. DAX also contains an in-silicon decompression engine, which is used to decompress data as it is being read from memory or cache at a high speed. And this inline decompression works in conjunction with query functions to further improve performance. DAX is a powerful accelerator. The query engine and the decompression engine are designed to maximize the utilization of all available memory resources, and hence they provide analytics at system memory bandwidth. So enterprise-class core, low memory latency, scale-out networking interconnect, and security and acceleration provided by these advanced software and silicon features make Sonoma a powerful chip for scale-out. Now let's look at some system design concepts using Sonoma technology. You can build a scale-out system using traditional rack mount servers. So the picture compares our current generation T5 processor rack mount server with the conceptual 2-socket Sonoma compute node. As seen in the picture, all the yellow components that are needed to talk to memory, I/O, networking, and InfiniBand are no longer required. DIMMs are directly attached to Sonoma. Storage is directly connected. InfiniBand links are running right out of the board. And even networking has been encapsulated by using Ethernet over IB offload, where Ethernet packets run over InfiniBand. So this design provides extreme density in rack space. And it reduces power consumption, and it increases reliability, as all those extra components and links are no longer required. And finally, it reduces system design cost. So how does the performance of Sonoma compares to the T5 processor that you just looked at? Looking at single-thread performance, 60% improvement in memory latency, 30% gains in integer performance, 2.4x gains in query performance using DAX, and 8.5x gains in decompression performance using the DAX decompression engine. So excellent improvement in performance across the board. Comparing throughput performance on a per-core basis, excellent improvement in enterprise throughput for Java, 60%, query, 70%, and 2.6x gains for OLTP plus analytics, where Core works on OLTP transaction processing, and simultaneously DAX works on query analytics. So again, excellent improvement in performance across the board. So in summary, a high-performance design, an extreme density in rack space that lowers latency, power, and cost, and increases reliability, makes Sonoma a perfect choice for scale-out. Now, this concludes my part of the presentation, and I will hand it off to Rahoul to talk about networking features of the chip. Thank you.
Thank you, Basant. Basant shared some of the compute side accomplishments on Sonoma. I would like to spend the next few minutes sharing with you some of the exciting things that we've done on the I/O side. When Sonoma was first being conceptualized, we looked at where we would like to target Sonoma. And we identified key features that we would like to incorporate for database, enterprise, and cloud deployments, which are a compelling and differentiated networking infrastructure that would address the demands of tomorrow's extreme scale workloads in lower cost form factors. For database and rack clusters, a highly scalable, low latency backbone with a 10x or better packet rate performance and a predictable quality of service. Improvements in end-to-end latency for enterprise application scalability with a predictable quality of service, enabling user-level inter-process communication with resource scaling for a large number of connections. And for the enterprise and cloud side, fabric consolidation to streamline data connectivity. These features drove the architecture and the design of this HCA that I will cover in the next few slides. The InfiniBand HCA is integrated into Sonoma as shown on the diagram in this slide. The design has two FDR ports running at 56 gigabits per second connected to a multi-threaded transaction controller via InfiniBand physical and link layers. The transaction controller connects to the coherent memory system via a PCI root complex and its I/O MMU. Via PCI, the HCA is made visible to software as a single root-aware I/O virtualized endpoint with support for 32 virtual functions. The HCA is compliant with OpenFabric's software stack and compatible with Oracle's database and applications. Sonoma provides a high availability, reliant, and fault-tolerant network connectivity and seamlessly integrates into Oracle's portfolio of products. The HCA virtualization enables 16 million queue pairs for each virtual HCA for virtual machine migration and scalability. The packet rate classifier is capable of supporting line rate traffic when both ports are running in an active-active mode. Now we have a couple of advanced features that we've put into the design too. Conditional RDMA and virtual cut-through messaging for high transaction efficiency. And for fabric consolidation and rack and database, we have multi-protocol support, such as IP over InfiniBand, Ethernet over InfiniBand, and a number of hardware offload and security features as shown in the list up here. Server, storage, operating system, virtualization technologies have been widely deployed in the enterprise, cloud, and data center, and are one of the key factors driving cost savings. Sonoma enables combining these technologies with network virtualization to further simplify the infrastructure and reduce cost. The virtualization framework in Sonoma supports the standard InfiniBand layer 2 semantics with our layer 3 extensions for extreme virtual machine scalability. A simplified view of the virtualization framework is how the logical domains connect to the HCA and how the HCA is viewed from the network side. As shown in this diagram, the logical domains connect to PCI functions via hypervisor. They are self-contained, have an open fabric stack, and an HCA driver. The user processes that are running within the domain have direct access to the hardware and can submit work requests when they want to communicate with other nodes on the network. This virtualization model also enables each logical domain to observe the device as a complete HCA with support for 16 million queue pairs. In addition, it has its own local ID and global ID tables. The view from the network side is that the InfiniBand subnet manager sees all of these logical domains, which are 32, because of our support for 32 virtual functions, as independent HCAs attached to a layer 2 switch. And the layer 2 switch connecting to the network via a physical port. Our layer 2 switch with its layer 3 extensions enables extremely fast packet forwarding with reliable multicast when the nodes are communicating with each other on the same physical HCA. So what are the key takeaways up here for us? We have a transparent virtualization for both the host and the network side. No reconfiguration of any forwarding tables across the entire fabric, and the user processes having direct access to the hardware for low latency and efficient CPU, OS, and network operations. We've covered virtualization. Let's see how differentiated networking has worked out for us. This framework solves and addresses some of our pain points that we have, and more. Let's take scaling, for example. It addresses 3. First, packet rate versus processes versus IBQ pairs versus memory regions and nodes. Second, IBQ pairs and IB contexts. And third, latency under load, which is we found to be a fairly key performance metric for us. We have an optimized hardware-software interface for low latency and efficient CPU, OS, and network operations. A transparent virtualization model with hardware-enforced security and isolation for the guest domains. Full 16 million Q-pair support per virtual HCA that enables migration of RDMA ULPs. And virtualized subnet management agents and general services agents. An MMU that has support for shared page tables and a fast path invalidation of MMU context via an inline work request mechanism. And we have multi-protocol support on a single interconnect. So this slide highlights one of Sonoma's Q-pair scaling and packet rate performance measurements that we have done. Enterprise applications such as database and middleware typically have tens of thousands of concurrently operating processes. And when these processes use InfiniBand as a transport to communicate, they use Q-pairs or QPs. So for efficient communication and for application scalability, performance, and response time, it is important for Q-pair scaling to be there. So how would we measure Q-pair scaling? Well, we take a simple packet rate test where we have a number of Q-pairs that are increasing so that we can measure the performance of the HCA. At the same time, it's important for us to maintain an almost flat latency profile during this entire test. As you can see from this chart, the packet rate linearly increases as the number of Q-pairs increase. And for a typical workload of 2,500 Q-pairs, reliable Q-pairs, we sustain a maximum packet rate of 55 million packets a second. It's a very, very impressive number. But since we were looking at not only having typical workloads, but also extreme scale workloads, we go to the extreme scale case where we have 100,000 reliable active Q-pairs. There, the packet rate reaches a steady state of 20 million packets per second. Low latency communication between pairs or groups of communicating processes in a cluster is key for enterprise application scalability and overall system performance and response times. Before I conclude this presentation, I would like to highlight why we are so excited about Sonoma. With Sonoma, We have brought an enterprise-class M7 SPARC processor into lower-cost form factors for use in enterprise and cloud. We have done this through the convergence of a number of features in the processor, such as common fabric for networking, integrated PCI, and direct attach memory. This convergence results in extreme density in rack space that lowers latency, power, cost, while also providing excellent throughput. Sonoma has several innovative features that we have covered in our presentation. Has an enterprise-class core with native cryptography support, security and acceleration with advanced software and silicon features such as ADI and DACs, and a low latency direct attach memory. In addition, the common fabric for networking and its ability to scale to tens of thousands of processing nodes with predictable performance in terms of latency, quality of service, and bandwidth makes Sonoma a perfect choice for scale-out. This concludes our presentation. Thank you.
Great, we have both presenters here to answer questions that the audience may have. Once again, the microphones are there. And please state your
NEC.
name and
I'd like to ask
affiliation.
you the latency of the InfiniBand.
Could you state your name and affiliation, please?
Satoshi Matsushita, NEC.
The latency of the Infinity.
Latency, yeah.
So we will be publishing these performance and latency numbers closer to when we do a product launch.
Thank you.
Nathan Brookwood, Insight 64. InfiniBand has been very successful in the high-performance computing segment, but that's not where Oracle plays. And I'm wondering, what is it about your customer base that makes you think that InfiniBand, that you're willing to dedicate such a big chunk of the chip to an integrated InfiniBand interface?
We don't expect our customers to break with the traditional networking model. We want to provide our customers with a choice. We have integrated this functionality within the design with significant amount of features and optimizations for scale-out applications, enterprise application scalability, and we will encourage them to adopt this technology because we feel the performance that you would get from this is excellent.
Well, InfiniBand performance has always been way better than the other alternatives, but that hasn't driven any market acceptance except in HPC. So again, why? What's different this time?
It's a lower cost solution with a large amount of integration. We have direct attach memory, integrated PCI to go for the traditional networking model, InfiniBand for an enhanced networking and scalability, and an enterprise class M7 processor.
Great, thank you.
And one more question.
Yeah, Bill Rash from Intel. Question I have is, what's the advantage of integrating the InfiniBand onto the die versus running it external over a PCI Express line?
Well, when you're closer to memory, we have much lower latencies associated with that. We can optimize the workloads, the performance, reduce cost, reduce power, real estate on a board. I mean, these are all high payoff activities for us. So it's beneficial for us to do an integration of this type of.
What kind of a latency benefit do you expect to get from integration?
We'll be able to publish a lot more of those numbers closer to when we do a product launch.
Okay, thank you.
We take one more question, Charlie.
Hi, Charlie Demergent from Semi-Accurate. Oracle now controls the whole stack from hardware, OS, and software. Basically, you can do it all as one piece. Any unexpected synergies and or anything you couldn't have done had you not had this complete end-to-end control?
So Oracle is a provider of the entire stack, from operating systems to databases to middleware to hardware, is in a unique position to provide unique values to our customers. And so based on our understanding of the entire stack and workload, we believe customers will benefit from having a part like Sonoma.
Okay, let's thank our speakers.
Thank you.
Okay, the next talk, the final presentation of the day, is titled I/O Virtualization and System Acceleration in Power 8. Our speaker will be Michael Gschwind. He is the Chief Architect and Senior Manager for Power Architecture and Power Application Software Interfaces, and the Chief Engineer for Machine Learning and Deep Learning. Mike has previously contributed to the development of Cell, Xbox 360, Power 7, Power 8, and BlueJean. He is an IEEE Fellow, an IBM Master Inventor, a member of the IBM Academy of Technology, and an ACM Distinguished Speaker. Let's welcome Michael Gschwind.
Thank you, Sam. I'm excited to be here today to talk about our innovations in I/O virtualization and system acceleration in Power 8 and for the open power ecosystem. So our industry has benefited and been driven by exponential price performance improvements for many decades, allowing to bring the benefits of information technology to many areas of human endeavor. However, as we find that the feature sizes in silicon are approaching the size of atoms, the improvements that can be gained from further reductions feature sizes is starting to taper off. So to continue on the path of exponential price performance improvement, architects increasingly have to turn to system architecture improvements, to improvements in service and system function delivery, and to innovate across the entire system value chain from semiconductor technology to services delivery by innovating new ways of accelerating workloads, by delivering new ways of accessing system capabilities, by employing advanced memory technologies, and with advanced networking and I/O acceleration. Since all of these technologies require optimizing across the entire stack, it is important to bring the various players in the industry together to collaboratively optimize the stacks to take advantage of these opportunities, which is why many of the major industry players have been joining the Open Power Foundation to innovate across an open ecosystem. So if you look at system design circa 2015, you'll see several trends. One is consolidation in the cloud to, on the one hand, get economies of scale of delivering compute capacity, but also to exploit dynamic load sharing and get better utilization out of systems. From a technology perspective, you'll find that this reduces largely to virtual machine aggregation and processor virtualization. We see I/O aggregation becoming increasingly important. This drives, from a technology perspective, both I/O virtualization and, of course, I/O isolation, that is separating the permissions, separating the data streams to ensure access control. And finally, data center architects continue to have to deliver performance growth for critical workloads under increasingly severe power constraints, area constraints, and cost constraints. So from an open power perspective, we're addressing these three dimensions of system scalability, of system capabilities, by standardizing three distinct architectures for processor virtualization for virtual machine aggregation. Those capabilities are built into the power instruction set architecture. For I/O aggregation, I/O virtualization, we have a I/O design architecture, and to enable architects to continue growing performance, we introduce a new coherent accelerator interface architecture. We have talked about the power instruction set architecture and the virtualization, CPU virtualization capabilities in past presentations on Power 8 here at Hot Chips. So today I'll focus on the I/O design architecture and the coherent accelerator interface architecture. So let's turn to the I/O design architecture. The purpose of the I/O design architecture is to deliver advanced I/O virtualization, and that includes I/O address translation. That comes in two different flavors. On the one hand, a single-level translation capability that supports contiguous Power VM partitions, where each partition uses a contiguous range of system memory, and but hierarchical translation that is designed to support Linux and KVM partition memory. KVM assigns memory to partitions dynamically, and so the memory map does not consist of contiguous areas of memory for each partition, but rather responds to the dynamic allocation patterns of memory to those partitions. The I/O design architecture also offers partition data isolation by presenting separate I/O address spaces for these partitions. And finally, it delivers partition fault isolation. Fault management domains based on partitionable endpoints mean that a fault on one adapter does not have to take down all the partitions in the system. So partitionable endpoints are a key management and partitioning concept in the I/O design architecture for power. A partitionable endpoint can consist of one or more I/O adapters that together form a assignable entity to a partition. A partitionable endpoint can also consist of virtual function interfaces of hardware virtualized I/O adapters, where each virtual function interface of an IOB adapter may be assigned to a separate partition. So, many of the I/O functions in a power system are tracked using partitionable endpoints. That includes the MMIO load and store address domains for accessing devices, the DMA I/O address spaces and I/O translation tables that map I/O accesses to system memory, the tracking of interrupts, the ordering of transactions within a partitionable endpoint, and partitionable endpoints are also error and reset domains. That gives systems using the I/O design architecture server class reliability and availability, because once a partitionable endpoint enters in an error state, once any device in that partitionable endpoint flags an error, all further transactions of devices associated with that partitionable endpoint are suppressed, giving the system a clean restart point and allowing the system software to reset and restart the I/O with a clean restart point. Partitionable endpoints and the tracking of errors and resets at the partitionable endpoint level also ensures that other partitions that use distinct I/O devices can continue to operate without interference as the system software resets and restarts I/O devices associated with a specific virtual machine. The I/O translation and supported for DMA memory addresses implements isolation of partition to ensure that I/O devices assigned to one partition can only access the system memory for that partition. It also creates a contiguous view of non-contiguous data in system memory. So if you have an I/O device that expects its buffers to be in contiguous system memory, that is something that can be presented to that I/O device, even if the data is non-contiguous and scattered across multiple pages that are not necessarily adjacent by way of address translation. Finally, the I/O DMA memory translation also enables 32-bit devices to be used without limitation in a 64-bit system, since the 32-bit address that the device would access can transparently be translated to any 64-bit system physical address. The processor chip contains a cache of most recently accessed translation and other IODA tables, and the full tables are stored in system memory to ensure scalability across a large range of system configurations. Let me now turn to some partitionable endpoint management primitives. First off, all DMA accesses are validated by checking the trusted requester ID consisting of the bus device and function number of a I/O adapter against the assigned devices for a partitionable endpoint, and mapping that to the untrusted 64-bit address, if you will, the address provided by the device driver. Also, interrupts are tracked in system memory as part of the partitionable endpoints, and so when an interrupt is received by the processor, it can be tracked in system memory. Finally, PEs are the I/O design architecture maps the requester ID to the PEs to identify which partitionable endpoints are affected by errors in a specific adapter and to stop all the transactions associated with that partitionable endpoint. In particular, for hardware I/O virtualized adapters, that means that if any PE, if a hardware virtualized I/O adapter is suffering a fault on its physical function interface that is of the hardware itself, all the affected, all the partitionable endpoints that have a virtual function interface of that hardware adapter transition to the hardware state to reflect the unavailability of the shared hardware resource. In many systems, the I/O subsystem is also used to attach accelerators into the system. However, we believe that one size does not fit all, and while the PCI primitives and the I/O hardware architecture is a very scalable resource for I/O, it is not the best abstraction to integrate hardware accelerators into the system. So to that aim, we have defined a new accelerator attach architecture, the coherent accelerator interface architecture that underlies the coherent accelerator processor interface, or CAPI. It's a new interface that we have introduced with Power 8. It is now available in every Power 8 system. It is targeting the acceleration of functions that do not fit the traditional CPU model, and it builds on a long history of IBM workload acceleration. As we're turning to building these heterogeneous system architectures, the 4 P's of system design, if you will, still need to be addressed, or heterogeneous designs need to answer those 4 4P questions. That is, how do you achieve programmer productivity? How do you realize performance benefits for a new architecture? How do you ensure portability? So if ISVs, if developers invest time and resources into supporting that interface to protect that investment in the future, and how to partition systems, multi-user systems across processes and partitions. To that end, the Coherent Accelerator Interface architecture supports fine-grained data sharing with a coherent and shared memory. It supports accelerator-initiated data accesses and transfers, again, to that coherent shared memory. It, very importantly, supports pointer identity. That is a shared view of the application and system memory between applications running on the CPU and running on accelerators. A pointer that can be used to access an object from a CPU accesses that very same object when used by an accelerator and to access the same memory. And finally, by offering flexible synchronization primitives that are symmetric and have programmable interfaces. So with these capabilities, coherent acceleration overcomes what might be called device driver deceleration. Today, if you're building an accelerator, the challenge is getting the data to the accelerator and then getting those results back. And those are non-trivial costs. So typically, in an I/O model flow, this involves interacting with the device driver, calling a device driver who then would either pin the data or copy the data to a pinned memory location, and then notifies the accelerator via the I/O interface. Then the accelerator does its work, and when the accelerator completes, there is the data has to be copied back and then provided as a return result from the device driver. All in all, we're looking at something like 15,000 instructions or more to copy the data to and from the accelerator. In summary, if you have an application piece of work that corresponds to roughly 45,000 instructions, and your accelerator delivers a 3x performance improvement, so it only takes the time of about 15,000 instructions. When you add the cost of data preparation and receiving the data back, you are left with only 33% performance improvement. So that has limited the benefits of accelerators in the past. With the shared system memory coherent model, the cost of communicating with accelerators and sending data to accelerators becomes much smaller, because the key operation here is to notify the accelerator, and then the accelerator will pick up its data from system memory, so it's a zero data copy operation, and the same, of course, on the way back out from the accelerator, reducing the cost of data prep and communication significantly. So looking at the capabilities for workload acceleration, we have designed several generations of workload accelerated systems, starting with compute accelerators in the cell broadband engine, and then building on that experience with compression, encryption, and random number generation accelerators in Power 7 Plus. And so as we were looking to take the next step, we found that SoC designs offer the highest level of integration, but in terms of addressing a broad range of acceleration opportunities, the challenge is that to deliver to the market new accelerators requires a new chip start, which involves long time to markets and requires very high volumes for such an accelerator to be viable. So starting with Power 8, we offer an interface that is modular and that allows third-party high-value add components to be attached to the system outside of the main CPU chip and participate in the coherence traffic and participate in the system interfaces. To that effect, we have a standardized layered protocol. At the top level, there's an architectural interface, and below that, there is a functional protocol underlying the CAPI interface, sitting atop of the PCIe signaling protocol to carry the actual electrical signals. By using this layered modular approach, we enable third parties to integrate accelerators with a faster time to market and a lower bar to entry, and supporting a variety of implementation options, either FPGAs or ASICs. Let me now turn to CAPI accelerator programming. So the key function or the key capability here is the accelerator's participation in virtual addressing. That supports pointer identity. So when you send data to an accelerator, that accelerator is able to access the objects, the very same objects that would have been addressed by the CPU. To that end, CAPI, the accelerators share the page tables and participate in address translation and invalidation traffic. Having the accelerator participate in address translation also ensures that each accelerator can only access the data that is associated with its application. And that is true both of the process level and of the partition level, of the virtual machine level in a system. Finally, the transfers that are initiated by the accelerators participate in the cache coherence traffic. So no memory pinning of non-cacheable memory buffers is necessary, and the accelerator can pick up the most recent data from whatever cache holds those data. From an accelerator virtualization perspective, there are three models supported by the coherent accelerator interface architecture today. One is the dedicated model, where an accelerator is assigned to one application by the operating system and the hypervisor. There are also two shared programming models. One, a time quantum model that is managed by the protocol, and where after a time quantum expires, the accelerator switches to process work requests from other applications. And the third model, where the accelerator picks the application that it wants to interact with. For example, that is an appropriate model for networking accelerators, where when data comes in, the accelerator identifies the receiving application process and deposits data into that address space. Let me now turn to three application case studies. The first example here is explores the impact of accelerator-initiated data access and the importance of that for scalability. So in comparison to traditional models where the data transfers are initiated by device drivers and ultimately the CPU, the accelerators in the coherent accelerator interface architecture are responsible for initiating that transfer. And that is critical to ensure scalability, because even for applications where data transfer is just a small fraction of the overall execution time, as you're adding more accelerators and exploit more parallelism, we'll find that Amdahl's law also applies to accelerators. That is, if you have one serial part that is confined to executing on the CPU, for example, the data transfers, as you add more accelerators, that becomes a more significant portion of the overall execution time. The second case study we looked at was to explore programmability and the flexibility of accelerator models. And to that effect, we decided to look at garbage collection. Garbage collection is the ultimate unpredictable pointer chasing application, if you will, where you follow addresses stored in heap objects to identify which objects can still be reached in the heap. So it's a highly unpredictable workload that does very little computation and a lot of system memory access. So it's the ultimate stress test for accelerator models. We find that with the pointer identity that it's quite tractable to implement garbage collection accelerators using this model. And they deliver significant improvements in area delay and power delay products. Finally, the final case study explores the benefits of accelerating the data sharing with the shared access to system memory by both CPU and the accelerators. For this example, we're looking at servicing NoSQL requests, and with the flash system, a IBM solid-state device system. And we are comparing two options using the same flash system, either attached via PCIe or via the CAPI interface. And we find that using the CAPI interface shaves about 19,000 instructions off the path lengths to talk to the flash system, yielding a 5x improvement in I/O operation bandwidth and a 2x reduction in system latency. And that enables us to to deliver the performance that commonly requires an entire rack with 6U in the rack, a 4U power server, and a 2U flash array. So to conclude, Power8 delivers advanced virtualization for both CPU and I/O. With high-performance I/O virtualization, it offers data isolation and fault isolation. Power8 also introduces a modular architecture for system accelerators that eliminates the overheads inherent in I/O models to access accelerators. It reduces the latency and increases system throughput. Based on what we believe is the importance of these interfaces, we are standardizing them together with our partners in the Open Power Foundation. IBM has donated both of these specifications to the Open Power Foundation, and they are available royalty-free for all Open Power Foundation members. With that, I'll conclude my talk, and I'll be happy to answer any questions. Thank you.
We can entertain one or two questions. Right?
Yeah. You talk about the acceleration by the way the memory is now shared. That's not a new concept. That's been used for decades and decades to build accelerators. It hasn't been maybe as standardized quite as much, but I've personally built quite a number of accelerators that walk the page tables of the host and so forth and got exactly those same benefits. As far as, I'm not quite sure what it is new here you're proposing, other than maybe a little bit more standardization than there's been in the past.
So I think the critical functions that you have to look at in a multiprocessor context is synchronizing any cached page table entries, tracking the coherence requests, making sure that you're getting the most up-to-date data out of caches. So having the accelerator participate in cache coherence, etc. Clearly, sharing memory per se is not a new concept. It's the architecture and making sure you're getting all the details right and providing that in a modular, standardized interface.
Well, yes, but I mean, the way this was solved decades ago was you just basically pretended you were a CPU and played all the coherency games and so forth, protocols and so forth, and you got those advantages. So that was used many, many years ago.
Yeah, as you were pointing out, I mean, there were special purpose solutions. They weren't standardized. They weren't delivering this through modular interconnects to external applications. But certainly, as I said, the concept of sharing data and memory per se is not what the innovation is, but
okay, I mean, it was modular in the sense that for certain systems, it just basically was follow these instructions and you're a CPU and you're modular and it all works. And that's been around for a while.
Okay, that concludes the time, and let's thank our speaker. Thank you.